In this video, we're going to do a strong acid, weak base titration. So for example, we would have a strong acid placed in this flask plus an indicator, because remember, you need to have something to tell you when the endpoint is reached. And we would have a weak base placed in the burette. If I was looking at the titration curve, I know I have a strong acid there because my pH is less than 7. And as I start to add the base, the pH starts to go up as per the green line. But then there'll be a region where there's a resistance in pH change, and that's again because you have a buffer that's set up between the weak acid and the weak base. And so if you have a buffer that's set up between the weak acid and the weak base, the conjugate base, then there's going to be a resistance of pH change. But once you go beyond that region, you're going to continue to increase, and there'll be a point where you're basically all reacted with your acid, and the increase in pH will happen much quicker. You'll have much more quickly. You'll have a steep region here. And then once you go beyond that steep region, you've overshot. So your goal is to aim for that steep region with your titration, and you want to aim for the equivalence point. So if we look at the middle of the steep region here, the green line, not the brown one, because it's a strong acid, strong base, you'll see that the pH is, and that's a bit of a poor estimate there, but the pH is below 7, which is what we would expect. The pH is below 7. So we would expect the pH to be below 7 because we have a strong acid, and we have a strong acid and I should have said a weak base here, a strong acid and a weak base titration. So in a strong acid weak base titration, you have a pH, an equivalence that's less than 7. And that's because the salt is going to be acting as a weak acid. And we'll take a look at why that is, as we've seen in previous videos. So here we have an example of ammonia being titrated with some hydrochloric acid. So what we have actually in this situation is our ammonia is in our flask, and the hydrochloric acid is in the burette. And so you can do that as well. You can have the acid in the burette, and you can have the weak base in the flask. In that situation there, if your weak base is in the flask, your titration curve will look a little bit different. It'll kind of be flipped. You'll have your pH starting off at the top here, so closer to a pH above 7, so maybe somewhere around here. And then it'll slowly start to decrease until you get to more acidic pHs because you're adding acid. So you can titrate that way as well. You don't always have to have the acid in the flask. So let's go take a look at the neutralization reaction that would occur here. So we have ammonia reacting with hydrochloric acid. Now, generally, when you have ammonia in a solution, we actually write it like this. It's actually ammonium hydroxide, NaOH, AQ. Some people write it like this. They'll put NH3AQ. But in reality, in a solution, it's actually NH4OH-AQ. And we're going to make it react, and you can choose any one of these to write with hydrochloric acid, the strong acid. And when you do this reaction, it's a double displacement again. So the H goes where the NH4 was, and the NH4 goes where the H was. So you get some H2O, liquid, plus some NH4 Cl aqueous. This is your salt. If you write it the shorthand way, you don't know where it's not apparent where the H2O was or where it came from or where it went. But this still works because the mole ratios are match. But just so you know, when we say ammonia solution, we mean ammonium hydroxide. So here we have our neutralization reaction, and we care about our salt as usual. So we want to show what the salt looks like dissolved in water. And so we'll take our salt, we'll write NH4Cl solid. We will put our equilibrium expression there, separate them. Ammonium is positive aqueous, and the chloride is negative aqueous. And we have to do a hydrolysis reaction to see how both of these parts of the salt affect the pH. We'll start with the chloride salt, and the reason I'm starting with that is because I know right away from experience that comes from a strong acid, so it won't affect the pH. I just have to show that. So if I was doing a hydrolysis with chloride, made it react with water, the chloride is negative, so it would combine with some H plus to make HCl aqueous. And then, of course, there's some OH left over. So the chloride would theoretically be acting as a base. However, what you'll notice is that this reaction probably won't go that way. That's because this is a strong acid. And this is the salt of a strong acid. So that means it's going to want to stay as Cl- and not reform HCl. So no effect on pH. Okay, so that one does not have an effect on pH. Therefore, no effect on pH. Now, suppose we have the ammonium salt, which we do. We're going to write an equation out for it, NH4 plus AQ plus water. And the easiest way to see what it forms is to look back at your initial equation. It's going to form some NH3. Okay, so it'll form some NH3 in an equilibrium. You could also write it as NaOH. That's fine as well. Or NH4OH, which would have worked out. Plus some H3O plus, or H plus is another way you could write that. So you'll notice that this here is a weak base. So this over here is the salt of a weak base, which means that it is acting as a weak acid. And that makes sense because we produce some H3O plus. We want to find the pH equivalent, so we have to do some calculations using the salt that affects our pH. So we're going to make an ice table. For this situation here, we don't care about water. We know that at the beginning, when we had our salt, we just had NH4 plus. We didn't have any NH3 or H3O plus. Then the change becomes plus X and plus X as long as it's balanced, and it is. And then we have X and X over here. Our change here would be minus X, but we need to figure out what the initial concentration of the NH4 plus is. So we need to somehow figure out how much NH4Cl was made, and therefore how much NH4 plus was made, and calculate that in the new volume. So here we gave you even less information than we did in the previous question. Let's see if we could figure something out. So we'll start off with using our ammonia or ammonium hydroxide to figure out how much of the NH4Cl we have. We'll just find the number of moles of this. It's in a 1-to-1 ratio with this, so we'll find the number of moles of that. And then once we have the moles of this, we can find the moles of this. That's pretty straightforward. We'll start with that. So we know that, okay, so let's go do that here. Concentration is equal to N over V. Therefore, N is equal to C times V, which is concentration 0.35 molar times the volume, which is 0.025, because it's 25 mils. 0.025 liters. Cancel out the liters, and you get, so 0.025 times 0.35, we get 8.75 times 10 to the power of -3 moles. Just double check to make sure that's right. So 0.025 times 0.35, 8.75 times 10 to the power of -3 moles, or you can write it in standard notation. So that's the number of moles of this that we have, or this, doesn't really matter which one you use because it's a 1-to-1 ratio either way. So since we have a 1-to-1 ratio, the moles of NH4Cl are the same. So we have a 1 NH4OH to 1 NH4Cl ratio. Therefore, the moles of the NH4Cl are the 8.75 times 10 to the power of -3 moles. And likewise, if you want to find the moles of NH4 plus, because that's what we care about, not the Cl minus, because that's not affecting our pH, it's a 1-to-1 ratio here too. So that means that we have that many moles of NH4, which is equal to the number of moles of NH4 plus, and I'll add this here. Well, we'll do that after. I'll put since we have a 1 NH4Cl to 1 NH4 plus ratio. So we found their moles of NH4 plus. Now we just have to find the concentration. So we know our concentration is C is equal to N over V, which is the 8.75 times 10 to the power of negative 3 moles divided by the volume. Now here's the problem. We want to find the pH of the equivalence, which means once your titration is done, once you've mixed the two solutions together. Your initial volume is 25 mils for the ammonia, but you need to figure out what volume of hydrochloric acid you used. Okay, so you have to figure that out so you can add the two volumes together. In the previous question, you were told the volume of both, but here you're not. The only thing you're sort of told here is that you did a perfect titration. So your mole ratios should work out. In other words, I need to use the moles of the NH4OH to find the moles of HCl. And then once I have the moles of HCl, I can use my concentration and moles to find the volume. And it's pretty easy because it's a 1-to-1 ratio. So let's go ahead and we have to figure that out now. So actually I figure out the volume. So we know that the NH4OH or NH3 is in a 1-to-1 ratio with HCl. Therefore, we have 8.75 times 10 to the power of negative 3 moles of HCl. And we know the HCl has a concentration of 0.60 molar. So we know that V is going to be equal to N over C because we want to isolate for V. So that's going to be 8.75 times 10 to the power of negative 3 moles. Whoops. Yeah, that's right. Over the concentration, which is 0.60 moles per liter. Cancel out moles, and you're left with volume. So divided by 0.6, and I get 1.458333 times 10 to the power of negative 2 liters. Now this is the volume of HCl that was added. That's the volume of HCl. Don't forget it was added to a volume of NH3. So I have to add those two volumes together. I'm doing the 0.025 liters. So our new volume, V2 we'll call it, or V new, V2, V total, is equal to the 1.45833 times 10 to the power of negative 2 liters plus the 0.025 liters. So plus 0.025. We want to make sure it's liters because we're doing molarity. Is 3.958 times 10 to the power of negative 2 liters. So now that I have that, I can plug this in here. Times 10 to the negative 2 liters. And I get, so 8.75 times 10 to the power of negative 3 divided by that volume, 2.210526316 times 10 to the power of negative 1 moles per liter. That is a concentration of the NH4+. So it was a bit of work there because the question didn't tell us directly the volume of hydrochloric acid. I could assume that the volume occurred in that stoichiometric ratio because we said that we did a titration to reach equivalence point. So we basically stopped at the end point. We didn't overshoot or anything like that. So there was no limiting or excess reactant in this situation here. And if you didn't do this in scientific notation, you might have done it with decimal places instead. You would have, for example, got 0.221 molar. Okay, so either way, what we get here is 0.221 minus x. And now we want to work to find our x value because that is our H3O+, which allows us to find our pH. Now here we have an acid, right? Because it's giving away an H, it's making some H3O plus. So we have to make a Ka expression. So this was our long step 1, our long step 2, and now we get to step 3 where we make a Ka expression. So Ka is equal to the concentration of H3O plus times the concentration of the NH3, because those are our products, over the concentration of the NH4 plus, which is X times X over 0.221 minus X. So that gives us Ka is equal to X squared over 0.221 minus X. Let's go see if our table provides us with the Ka of NH4 plus. If it doesn't, we might have to look for NH3 and then do the relationship there. So we have NH3 here. There's a Kb for it. We could do the Kw over the Kb to get the Ka, but I'm going to double check just to see if ammonium's there. And look at that. It is. I'm going to save myself some work. It's 5.6 times 10 to the power of negative 10. So that's our Ka value. 5.6 times 10 to the power of negative 10 is equal to X squared over 0.221 minus X. I'm going to do the 100 rule test because I want to save myself some time here. So it's the initial concentration, 0.221, over the Ka value we just found from the table, 5.6 times 10 to the power of negative 10. And if you do that, you'll see it is greater than 100. Therefore, we can simplify. And so now we get 5.6 times 10 to the power of negative 10 is equal to X squared over 0.221. And if we continue this, we get X squared is equal to 0.221 times 5.6 times 10 to the power of negative 10, because I'm isolating for X. And then this gives us X is equal to the square root of what we had above there. So 0.221 times 5.6 times 10 to the power of negative 10. And that's going to give us, so times 5.6 times 10 to the power of negative 10. We'll do the square root of that. And we get 0.000011126, or you could write that in scientific notation, molar, which is our concentration of the H plus or H3O plus, same thing. So we got our concentration of H plus now. We got our X value. That's what we're looking for over here. So now our last step is just to find pH. We know pH is equal to the negative log of the concentration of the H plus or H3O plus, same thing, which is going to be the negative log of this 0.000011126 molar. So negative log of that gives us 4.953658142. So this over here is our pH. Therefore, pH is approximately, let's see, how many sig figs do we need? We need 2 sig figs. So 4.95 would round to 5.0. And this would make sense because we want a pH that's less than 7, since we have a titration of a weak base and a strong acid. Now, again, this titration curve is not quite the best representation of this particular problem here, of the problem that we did over here, because what we had in this situation was the base is in the flask instead, and the acid is in the burette. So it should be a little bit flipped. It would kind of look like this. I'm going to do a rough sketch. In another video, I'll show you a better one. But it'll essentially be, you start off with your pH that's higher than 7. And then you go down like that. And then your equivalence point would be lower than 7, which makes sense. And then if you overshoot, you'll be very acidic. And that's, again, because in this situation here, we had our base in the flask. So we had the NH3 in here, and then the acid was in the burette. So the HCl over here. And so when you're monitoring the pH change, you're going to start off with a more basic pH. then as you add the acid, your pH decreases until you get to your equivalence point region, and then the overshoot region happens there. This situation in this graph is if you had your acid in your flask and you're measuring that first, and then you're adding your weak base after. So this is our weak base in the flask, this is our strong acid in the burette, and we would get a figure that looks like that. So in this video, we saw how to calculate the pH at equivalence point for a strong acid and a weak base titration. Very similar to what we saw in the previous video for a strong base, weak acid. The main difference, though, is that you actually get a salt that's acidic. So you're using the Ka, and you're just finding the H3O plus directly to do the to find the pH. So it's a little bit easier than the previous example, because in the previous example you had the OH, and then you had to find POH and then find pH after that. The only additional thing that was a bit complex here is we didn't give you the exact volume of HCl, and so you had to figure that out. So please make sure you practice this problem until you grasp it fully. Once you're done practicing this problem here, you can go and try worksheets and other practice problems, but please make sure you understand these two very well until you don't need any more support to do them. And then at that point, you've understood titrations at the grade 12 level.